Okay, so students, we're back, and this is Lab 1. This is kind of part 3 video of Lab 1. And here we're going to interpolate rainfall where we don't have data across the state of Utah. We're using the rainfall gauging stations that we do have. And so to do this work, I've downloaded a state of Utah shape that you see here. And you could get that from the Utah Geographical Referencing Center. But I went to browse, add data, and then I can't remember if I got it from the Living Atlas or ArcGIS Online, but either way, you can choose those and search and download those directly and use features that you find in there for quick and dirty clips that you might need. Okay. So I've loaded that shape in the Utah boundary. One thing that you should be aware of to try to clip such features during the processing in ArcGIS under the Environments tab or after the fact as a raster clip is that sometimes these features have masks. So I'm going to check for that here. And you can see right now that mine only is the polygon of the state of Utah. Sometimes you'd find another object ID and it would be a mask that would be covering up stuff in the background outside of Utah. And if you didn't make an appropriate selection or subset this, and then use this as a clip file, you would not get your expected Utah boundary clipped the way you want. So be conscientious of that. If you do get such a thing, you can select the feature. You could right-click, data, export to a new feature that didn't have that mask, or you should also just be able to select and then run your process and only run it on the selection. Okay, so that's one thing. Other thing that we want to talk about in this video is then how to do the interpolations. Where do you find those tools in ArcGISPro? And then also, how can we kind of tune those a bit? So to find the interpolation tools, and you have to do this for both the Utah normals and the 2021 and 2022 data. But right now I've only brought in as points the Utah normals data that you saw in video 2. So I'm going to just run the interpolations, the 3 that we need to run on the normals, because that's our first step to decide which of those interpolations works best. So to find the interpolations, go to Analysis, go to Tools, and they're going to be under Spatial Analyst Tools, Interpolation. You'll find all the tools that you want. If I had just typed interpolate and it pulls up tools, and you can find that they'll show up under Spatial Analyst Tools, 3D Analyst Tools. Some things are under Data Management Tools. Remember that ArcGIS or Esri sells a lot of different toolboxes to different organizations. You have most of these toolboxes available to you, and some of them have the same things within them. So right now I'm telling you to use Spatial Analyst Tools. If we hunted around in 3D Analyst Tools, we probably find, yeah, the same things. Under 3D Analyst Tools, raster, interpolation, you're going to find all the same tools. So that's why in the lab I told you 3D Analyst Tools, but when I was showing people in class, maybe it's a little bit easier to navigate from Spatial Analyst to interpolation. Okay, so in the lab I asked you to use IDW, Spline, and Kriging. There's other options, as you're aware of from our lecture, but just to keep things reasonable, we're going to compare these methods. So first I'll try IDW. So remember that's inverse distance weighting. So to do our interpolation, we need to point at our point files. And then this is what you have to specify, the Z field. And the Z field that you want is, in this case, not elevation because we're not interpolating interpolating topography, we're interpolating precipitation. So I'm going to choose the annual precipitation. And if you don't change the output raster name, it'll go directly to your geodatabase for your file that you're working under. And we can see the output cell size shows as like 10 to the -2, so 0.02. And like, what units are those? They're probably degrees, because I remember that my points were in latitude and longitude, so I use World Geographic System kind of coordinate system. If we wanted that to change, we can choose output coordinate system, maybe of the Utah, no, not the Utah boundaries. So I would have to choose something if I want it to be meters that was projected. So if I go to projected coordinate systems, the common one you're going to want is UTM, North America, NAD 83, 2011 referencing system, zone 12N, say OK. I think it's going to want us to choose a geographic transformation, so I'll do that. So I'm going to type in WGS and scroll down. So I'm going to do this WGS to NAD 83 2011. Okay. So environments tab is really important during your geoprocessing because it allows you to get the output coordinates of what you want. You can also select the processing extent. And in the lab, I told you that I wanted to fit to the state of Utah boundaries. There's two ways you could go about this. You could process it all without the state of Utah boundaries, and you get a square. And then you can cut that square like a cookie cutter after the fact with a tool called Clip Raster. But I'm going to try to do it right in here. And so then I can say I want to follow the extent of Utah boundaries. But if you look here, that looks like a square too, right? It's a rectangle with top, left, right, and bottom defined. And then we get the extent coordinate system shown there. If we want it to clip to the shape, then we choose this mask and choose Utah boundaries again. I have it selected. It says use selected records. That's fine. So that's another way to choose or not to choose the selection. And so now we've set all these environments. Let's go back to the parameters, because now we can see the output cell size is in UTM coordinates of meters. And we see that it's about 1,783 meters. You don't have to accept this. This is just some algorithm choice based upon the distribution of your points and what seems reasonable. I like to have nice round numbers in case I want to do back of the envelope math on things after the fact. And you could choose something maybe like 2 kilometers, which would be 2,000 meters. Okay. And so then inverse distance weighting to the power of 2, you can change that. So you could say more strongly weight nearby points. That is up to you. I'm going to leave that as default. What it's going to do is the number of points, it's looking for the 12 nearest points. And it's going to do variable distances. So the search radius is going to be variable until it gets to finding 12 points to do the interpolation. So that will be helpful, like when we're way out here in western Utah, and there's points that are like 50 kilometers apart. So it's going to look for the 12 nearest points to learn about this point, but it's really going to worry about the nearby points. So if we're interpolating like right here, it's going to worry about that one way more than that one. And this is fine. We can go with that. If you didn't want to include 12 points, like maybe the interpolation doesn't matter once you get past a certain distance. So I could say like maximum distance to look, maybe 50 kilometers is a good number. We don't want to go further than that. Okay, so because, storm size or something, right, matters. Although a lot of Utah's storms are huge winter storms, so maybe then that's too minimalistic. But either way, it's a model. I'm going to go with that. 50 kilometers would not be this, right? It would not be 50. That's in meters. So I'd need to go 50,000 meters to get to 50 kilometers. So let's run that and see what happens. So it takes a minute to process these, even on a pretty good computer. So be patient with the computer. Okay, so there you can see the result there actually ended up yielding some holes, right? Because there are some areas of Utah where the nearest rain gauge is not within 50 kilometers, so we couldn't find any points to interpolate off of. Okay. So if I remove that 50 kilometers and I run it again, and then we have no kind of limit, let's see what sort of numbers we get. And you can see that, by the way, that it did produce the barriers. Okay, why isn't it showing up? Still has holes. I have to run that again. So let me remove number 3. So this one had holes. We wanted to fix that. And okay, let me fix it. Let's look for 100,000. I think it's a little bit glitched because I put a maximum distance, then I removed it. So this one should have no holes. I think usually if you leave default maximum distance empty, it'll just keep searching till it finds something. Okay, so this one looks pretty good. And I have run the one without any maximum distance. This looks quite similar to that, and that's probably what you will run. And so we can see that there's more rainfall along the mountain ranges, along the kind of higher topography, where we have a lot of rain gauges, and less, which is weirdly colored green, out here in the deserts, which seems reasonable. In some areas, we see a really kind of bullseye effect. That's probably high topography, nearby low topography. So you're seeing that inverse distance weighting effect, where that high topography is being weighted more. And so we get these kind of bullseye higher precipitation values. Okay, so I'm going to remove number 2 because it had holes. And so there's my IDW of Utah norms. Let's try another one. So we'll go back to interpolation. Let's do a spline. So we'll input our points. Again, we have to change that Z field. And I'll do just spline underscore Utah. And well, let's make it Utah norm like the other one. I'm going to go again back to my environments, and I'm going to now match the coordinate system of the IDW. And I guess I should specify that again. So WGIS, I thought it would default to that. Okay, so, and now Utah boundaries, mask, Utah boundaries, go back to parameters, and change our cell size to 2000 again to be consistent to 2 kilometers. And now it says that it's a regularized spline, or there's also options for something called a tension spline. What does that mean? You can click the info button to get a little bit more information. So regularized use a smooth surface and smooth first derivatives. Tension tunes the stiffness of the interpolant according to the character of the modeled phenomenon. So it sounds like tension is more sophisticated and potentially going to give you a better result. Um, if I choose it, I bet I get more options. Let's see. No, interesting. I'm going to keep it unregularized because it's the default and probably what most of you chose, but you could check them out and see how they do. I don't like, so the weight, when regularized option is used, it defines the weight of the third derivatives of the surface in the curvature minimization expression. If the tension option used, it defines the weight of the tension. The default weight is 0.1. And number of points means the local approximation use the nearest 12 points. Okay. So I think that we're good to go. We've got our 2-kilometer grid. We've changed the environments to the other coordinate system in the state of Utah's boundaries. Run. So we've got the name nicely organized for Spline, Utah norm. Yeah, I got a lot of negative values. So that didn't come out very good. So, if I just stayed with this basic spline, I'm not going to choose this as my option because if you look, it's got huge values, greater than any rainfall values that we actually saw in the original data, and it's got a lot of negative values. Across all of Utah, there's like huge negatives, okay? So maybe we should try a tension one and see if that does any better. And I'll just overwrite this file. Now we're seeing the IDW in the background. It's running. Okay, so the tension spline did way better. It held things more true to the data. And so I would recommend that all of you, if you are going to use a spline interpolation on kind of realistic data like this, you probably want a tension spline, and you probably would want to tune it maybe even a bit more. It does have a few negative values. I guess we could go in after the fact and turn anything that was negative into 0 in raster calculator. And it does produce values above any observed points. That's not completely unfathomable, right? That you could have higher rainfall values outside of the rain gauges. But I see where it's putting them. A lot of them is like areas where we have no data on the edge of the map. So it's like a boundary effect. So it's kind of an artifact of the model. But we'll leave it as is. That was our spline. Now we'll go to Kriging. And it says the empirical Bayesian Kriging provides enhanced functioning and performance. So actually, I'm going to choose that. I'm not sure where that's located in the toolbox. So I'm going to click on it here. And I'll go back to my points. My Z value again is the rainfall. And output coordinate system, the same as those ones. Same transformation. And output extent to Utah boundaries with a mask of Utah boundaries. Okay, go back to parameters. Cell size, I'm going to again populate it at 2 kilometers or 2,000 meters. And output the raster as EBK, Empirical Bayesian Kriging, underscore Utah norm. Okay. And it wants an output geostatistical layer, so it can tell us what it did. EBK stat Utah norm. Okay. And so then it has options. Transformation type to apply to the input data. Do not apply a transformation as default. Empirical. Multiplicative skewing transformation with empirical base function. Log empirical. Multiplicative skewing with a transformation of log in empirical base function. All data values must be positive if this option is chosen. All predictions will be positive. I like that. Maybe I'll do log empirical. And then semi-variogram model. Power, linear, thin plate spline, exponential. If the transformation type is set to none, only the first three semi-variograms are available. If the empirical or log empirical, the last six semi-variograms are available. So it starts with empirical. And so I'm gonna leave it on. No, it starts with exponential, sorry. For more information, see the topic on what is empirical Bayesian Kriging. So I'd recommend that you look at that before you make this choice. I'm not going to do that in this video. I'm going to leave it with the default. And there's other things, right? We could say how many neighbors are going to look at. Max neighbors, 15, min neighbors. Maybe we don't need that to be so many. It's got a weird radius, which doesn't look very big if that's really meters. Oof. Let's see, or maybe it's standard circular. So let's see, max neighbors, 15, min neighbors, 10. Maybe let's change that to 6. We could do 15, I guess, is fine. I don't know. I'm going to up this radius. It's kind of not sure what that means. Maybe it can tell me here. What's the radius? Radius is the length of the radius of each circle. Is the each search of the search circle. So it should not be, it acts like it's stuck on the degrees, like it didn't populate the kilometers. So I'm going to up it to 100,000 meters and see if this works. Don't like that. Oh, its default search radius is degrees. Okay, so I'm going to back that down. Then that is 100,000 meters, about 1 degree. I'm going to pop this to 2 degrees. Okay. So that always uses degrees, even if you change the coordinate system. Interesting. And there's other model parameters, maximum number of points in each local model. Yeah, a lot of statistical tools that you can tweak here. So this is, the reason that the actual Prism data uses Kriging in a very sophisticated way, also inputting something about elevation. But let's go ahead and run it with what we've done here. So far, of the two that we've run, I like the IDW better than the Spline. So I'm actually going to turn off the Spline. So we are looking at the IDW as we see this EBK interpolation pop up. See if it looks realistic. We forced it so it can't be negative by choosing the log empirical data transformation type. See what we get. Okay, interesting. So it's got a different color scheme, so it's hard for us to see exactly what's going on there. Maybe I can change that. So if we go and we look, well, if we just look at the range of data, that's a lot more similar to IDW. We got the same number of classes, but let's put them both on the same Symbology. And for now, I'm just gonna like match the symbology from the other file. So I'll get that from the IDW, say run. Okay, so it took a minute there graphically. So now I have EBK, should be on top of IDW. Where is that? There's my IDW. And so we can see like this region of high precipitation all throughout the Uintas, the Wasatch Front. Now I'm going to add the EBK on top of it. Seems to be taking quite a while to show these for some reason. I'm going to turn off my world hill shade, see if that helps. So EBK is a little bit tighter. So it seems like the mountains influence isn't as wide reaching on the EBK. Which is probably more realistic, right? Because the mountain ranges actually, on the Wasatch at least, aren't that wide. And then the mountains out here in eastern Utah are much smaller. And so I think that the Empirical Bayesian Kriging is doing a better job. So I'm not sure what you all chose, but I think this is probably the best of the three interpolation methods that we used. So that is what I'm going to use on the other ones. So I'm going to take some notes on the parameters. If we go back to that we used. So I should have written that down. So hopefully you do write that down when we're in the Kriging, right? What did we use here so that you can apply a similar method, since we have the same points, to all of the different tools that you use. So you're going to load in points for 21, 22, like we did for the Utah normals, and then just run your preferred of these three on those. So just one. So for me, I like the Kriging, and I'm going to go with that. So I'll stop this tutorial for now.